Starting a string trimmer or any small internal combustion engine using the conventional pull cord mechanism requires a great deal of upper body strength. Such a task is difficult for operators with limited dexterity or arm strength. Goodwill Industries, one of Trinity Engineering Science Department's non-profit collaborators, has expressed the difficulty faced by its employees while starting string trimmers with pull cord mechanisms. If Goodwill cannot secure a more user-friendly starting mechanism, people will continue to be sent away from available work. To complete this project, a 10-step engineering design process was adopted. As a first step, the problem is identified in terms of concrete parameters. Then the four major design constraints relevant to the problem are established. These include monetary, safety, mobility, and durability constraints. Research is done to investigate existing and relevant solutions. As a part of brainstorming, the group came up with designs involving an electric motor, actuators, solar cells, and pneumatic mechanisms. In the next two steps, the practical designs were filtered out and their models were tested. A decision matrix allowed us to choose the best solution based on ratings done using our design criteria. Exact dimensions, parameters, and components of the optimal design are specified. The design was then implemented. We improved the design by testing it and obtaining feedback from Goodwill Industries representatives. The design consists of three subsystems, which are the energy input, energy storage, and energy release subsystems. When an operator pushes down on the plunger, the gear turns in the clockwise direction. The gear in turn rotates the axle in the same direction. When the operator releases the plunger, a linear spring restores it to the starting position. While this occurs, the gear turns in the counterclockwise direction. A single directional bearing between the gear and axle makes this a free spin, allowing for the gear's motion without turning the input axle. This prevents the system from discharging before the maximum energy has been achieved. The user can repeat this process until sufficient power is stored in the spring. It should not exceed 30 plunges. Clockwise axle rotation winds the power spring. This spring converts the mechanical energy provided by the user into spring potential energy. The ratchet mechanism consists of a small gear, single directional bearing, and a rack. This setup allows for the axle to rotate in only one direction. It also allows the rotation to charge the spring without releasing the stored energy. When the rack is depressed, the output axle is allowed to rotate and the potential energy in the spring is converted to rotational kinetic energy. An important element to the function of all these components is the clutch mechanism. The clutch provides an auto disconnect between the input and output axles. This allows the axles to lock and move in the required directions for the function of the design. Additionally, it increases the design efficiency as it allows the device to deliver the power necessary to start the string trimmer without wasting energy on turning the gear on the input axle. To make this design functional, an attachment mechanism subsystem was necessary. A detachable design was chosen to prevent the operator from carrying unnecessary weight. This encompassed an aluminum claw that acted as an interface between the string trimmer and the design using latches. Certain design criteria had to be met to start the string trimmer engine. Initial values for these criteria were determined by testing the string trimmer. The crankshaft within the string trimmer required 54.9 inch-pounds of torque at an angular velocity of 800 RPM and must be rotated through 3.5 angular turns. Research determined what was a reasonable weight, size, and production cost for an alternative starting mechanism. Once the final prototype was constructed, it was tested and compared against the design criteria. The device met the torque, angular velocity, and size criteria. However, the device did not meet the angular turn, maximum force, or weight requirements. The device met two of the four design constraints specified at the beginning of the project. The device was developed using less than $1,200, and it safeguards the user from injury with its aluminum casing. The mobility constraint was not met as the device was heavier than permitted. However, the device was made detachable to address this issue. Finally, the durability constraint was not verified due to constraints. Unfortunately, the design was not successful in starting a string trimmer. Thank you, Dr. Nichols. Thank you, Dr. Leifer. And a special thanks to our mechanical technician, Manuel Garza.